First, let's understand what is a minor of a matrix is. Okay, minor of a particular element in the matrix is nothing but the determinant of a matrix. Okay, determinant of a matrix that is obtained where when row and column of that matrix for that particular elements is deleted, that is a minor. For example, if you want to calculate the minor of the first, here they have shown a second element a12, then you will have to ignore the first row in which that element lies and the column in which that element lies, and you have to take a21, okay, a23, a31 and a3, so a33. So this way you will get the minor. Okay, so minor is nothing but the determinant of a matrix. Okay, for again minor is calculated for particular element. Okay, minor of a matrix for any particular element is obtained by deleting the rows and columns of that element and taking the rest of the elements. Okay, for example, for a11, delete the first row, first column, you will get these four: a22, a23, a32 and a33. Okay, these four, this is 1 2 3 4 for a11. Okay, you have to delete the first row and column. So that is the minor of a matrix. Now what is the rank of a matrix? Rank of a matrix is nothing but the highest ordered non-zero minor. After you calculate the minor, whatever the highest non-zero minor you get, that is called as rank of a matrix. Now rank of a matrix, you have various methods of calculation. You can go through this article, very nice way they have explained. For example, you have matrix 1 2 3 4 5 6 7 8 9. Here you can see it's a square matrix and very easy to find its determinant. So hence the determinant is nothing but, for first element the determinant is nothing but 5 nines are 45 minus 8 six are 48. So that is what is written here. And for element 2, it is 9 fours are 36 minus 6 sevens are 42. So that way they have taken. And likewise for the third element, finally you will get the determinant as 0. Now this is 0 still doesn't mean, so this is still determinant, not the minor. So now because the determinant is 0, now you can see, you can find, so basically the order, what is the minor for this order is 2 comma 2. Okay, so 1 2 4 5 is taken, 1 2 4 5 is taken as the minor. Okay, this is the minor. So again, rank of the matrix, you can go through all this elements. Okay, now because the minor is 2 comma 2, very important, because the minor is minor determinant, sorry, the minor of the matrix, this matrix is 2 comma 2, hence the rank becomes 2. Okay, hence so the rank is 2. In other words, in much simpler way, okay, if you don't wanna if you wanna understand this in much simpler, much simpler way, rank of a matrix is nothing but the number, it's one of those values, either it's the row number of rows or it's the number of columns. When it is number of rows is when m is greater than n, it is columns. Okay, when number of rows are more than number of columns, then number of columns become the rank of a matrix, hence we call it full column rank. And when m is less than n, okay, then the it becomes a rank of a matrix will be the m value, hence it's called as full row rank. For example, we will see, um, okay, minor of a matrix, even before I go to rank of a matrix, how to solve that programmatically I have added here, because there is no direct method to calculate minor of a matrix. Okay, so minor of a matrix, as we know, we just saw, we have to delete the rows and delete the columns of a matrix in which the element exists. Okay, if you're talking about the first row and first column, let me make this as first element. So first row is this, and first column is this 147, hence we are talking about 1. So if you want to calculate the minor of 1, then you will have to delete this 1 2 3 4 5, sorry, 1 2 3 and 147, and if I execute this, you will get 1379. Okay, this is which value is it calculating for? One moment. 1 comma 2, first row, second column 2. Okay, for 2 it has to give 137 1278. Okay, maybe there is some issue with the logic, but as you saw here.
No, no, there is not. No, no, the issue is not with the logic. It is actually 1 comma 1. So it is taking the like 0 1 2 and 0 1 2
Oh yeah,
rows,
yeah,
0 1 2
okay.
columns. So it is for 11 5. So it is 1379. It should be.
Yeah, you're right. Okay. Yeah, so the indexing is starting at 0. Okay, my bad, sorry. So indexing is starting at 0. The first element is not 1 and 1, instead it is 0 comma 0. Okay, so if you take the element as 0 comma 0, you'll get 5689. That is the minor of the matrix. Okay, this is how you can get the minor. Okay, deleting the ith row and jth column. So if you just pass the value, you'll get the minor. Now because this minor is 2 comma 2, okay, minor is 2 comma 2, so clearly you can say, because the rank of this matrix is 2. Okay, so you can okay, we will see how to calculate the rank as well. Okay, if I just take this matrix, um, np dot, I need to, okay, I need to check what method it is, but you can calculate the rank of a matrix directly. Rank underscore matrix we have, but I need to check where where it is located in the um, numpy module. But anyway, so again, coming back to the rank of a matrix, so this is m by m matrix. What you saw here is m by m because it is 3 by 3, right? It is a 3 by 3 matrix, hence you have this m by m. Hence you can directly say the rank of a matrix is m, which is ultimately, after calculating, you get the minor, which is your 2. Rank of the matrix for this becomes uh, 2, min of m comma n, right? So we will see how to check, calculate the rank. Okay, and once you calculate the rank, you will be able to um, okay, one moment, let me show this with example. np dot random dot rand n. Okay, let me take m and n. So we will vary the values of m and n accordingly. First, let's set the value of m comma n. M comma n is equal to 4 comma 6. Okay, for initially we will consider this, and this is our a. If you print, you will get a. Okay, and or maybe I'll take a rand int. Okay, fine, we'll go with this only. If you want, I'll round it off, entire thing by 2 elements. That's enough for us. Okay, yeah, much better. So okay, so once you have this array or the matrix, okay, so you can calculate np dot uh, linear algebra dot, okay, there it is, power rank. Okay, matrix rank of a. Okay, so if you print ra, you'll get 4. So it has a rank of 4. Okay, rank of 4. So if you notice, if m is less than n, so this rule applies, third rule applies. So if m value is less than n, then the rank of matrix becomes m. hence this has a rank of 4. Okay, and likewise if you modify these, um, let's make this as 6 comma 4. You reverse the number of rows and columns. Okay, um, yeah, rank is still 4, so m is greater than n, so then the value should be n. Okay, so if m is greater than n, then the this second rule applies. If m is greater than n, then the rank becomes n. So basically, in a way, if you notice, whatever is the minimum value, that is the rank. That is what I am inferring from this. Okay, let's try test it out with 4 comma 4, then also rank will be 4. Okay, basically what you have to understand is, if they are same, that is the rank of the matrix. If these rows and columns are same, then that is the rank of the matrix. If rows are higher than columns, then because whichever value is smaller, that is the rank of a matrix. So because rows columns are less, so that becomes the rank. If rows are less, columns are more. Okay, so whichever is the smaller value, that becomes its rank. Okay, so is this clear? Rank of a matrix.
Yes.
Okay, all right. Next, look at how to reduce the rank. Let me check the topics. One moment. Okay, yeah. So this is fine. This is the rank of a matrix. Next thing is, we will see. See, minor we don't have a direct method to calculate, but determinant surely we have method to calculate. So let's take the same A matrix that we just created. If you first of all, if you want to calculate the determinant, um, okay, let me apply and then I will explain. Lin alg, uh, okay, dot, okay, determinant of A. So determinant of A, as you can see, you got an error because it's not a square matrix. Okay, so that's why. If I had a matrix like this, I wanted to show you deliberately. Let me take a different one. Np dot random dot rand n of 3 comma 3. Okay, this is our matrix, and if I want to calculate linear algebra package, we have dot determinant of A. Okay, so this is the determinant of A. Now determinant of A is nothing but, okay, so determinant of A is nothing but is just a number, okay, applicable for square matrices, and it is used for analysis of linear equations and their solutions. Here is the definition. It is nothing but it is equal to summation of the product of elements of a particular row and column. Okay, for example, if this is your matrix, then the determinant of A11 is nothing but A22. Okay, where is that? What happened? Okay, determinant of, okay, we will see for a simpler class. Determinant here is nothing but multiplying the elements of diagonal and minus multiplying the elements of diagonal in other direction. Okay, BC. Okay, so that will give you the determinant. But for a 3 by 3 matrix, as you can see, A into EI minus FH minus B into DI minus FG, okay, plus C into DH minus EG. Okay, so determinant is a this is a formula again for Determinant you can go through your practice sessions, or you can just take one example and write it, just to get understand how this works. Okay. But it's simple enough. The same concept of minus work here. If you want to take calculate the determinant for a 3 by 3, you just have to eliminate this row and column, and whatever is remaining, for that you have to multiply and take the difference, and then multiply with this element. So that if you continue, again also notice these symbols. For first elements is plus symbol, minus symbol, again plus symbol. So this you don't forget. Okay. So that's how you calculate the determinant. But for us, we don't have to worry because we have a direct way of calculating. um, okay, fine. So yeah, you have some, if you want to like to know more, you can just go to this link, and you can practice there. Okay. So for us, we have direct way of calculation. Any questions with determinants?
No.
Okay. So here I will add determinant. Okay. Next is inverse of a matrix. Okay. Now for inverse of a matrix, um, we have a concept called A into A inverse. I won't be able to type the inverse, but you just understand. Okay, let me type INV. A into A inverse should be equal to identity. Okay, identity matrix. Or if you, let's look here itself. Um, okay, so inverse of a matrix is nothing but a matrix for any A matrix. Okay, A inverse is the matrix that exists upon multiplication to its original A, will give you identity matrix. Okay, A inverse is nothing but, if you want to see the exact formula, it is 1 divided by determinant of A. This is determinant of A, not modulus of A. This is determinant of A into adjoint of A. Okay, now we have to understand what is adjoint. Okay, uh, adjoint. Okay, adjoint of a matrix is nothing but, um, is the transpose of the cofactor of a cofactor matrix of B. Okay, if you want to understand, let's come from cofactor then. So cofactor matrix, um, okay, cofactor of a element in a matrix is obtained by minor multiplied by minus 1 into I plus j. So first, you know the minor calculation, so you just are eliminating the, for whatever the element you are calculating, you are eliminating those rows, and rest of the matrix becomes the minor of that particular element. Okay, and the complete, if you calculate the minors for all the elements in that fashion, that will become your minor matrix, and that minor matrix multiplied by minus I to the power of I plus j. Okay, so that will give you your cofactor matrix of that element. Are you following me?
Yes.
Okay, for example, here they have simplified. If this is your matrix, they are trying to calculate the minor for this element, which is your this element into this element, this element, this element, and this element. That is your minor for A12. Like this, you have to calculate the minors for all the elements. That's what you see here. M11 is the minor for A11, which is A22, A23, A32, A33. Okay, and minor for A12 is here. A13 is here. So that way, once you obtain the minors for all these matrices, okay, you will get the minor matrix. Now to that minor matrix, if you multiply minus 1 to the power of I plus j, where I is the value of rows, j is the value of columns that it is in, that particular element is in. For example, this is the first element, hence this is the first row and first column. So this is the first row, second column, this is the first row, third column. So that way, if you keep on multiplying, then finally you get cofactor of that matrix. Now after you get cofactor of that matrix, you have to take the transpose of that cofactor, okay, and then you get the adjoint of a matrix. To that adjoint, where is that, what happened, where is the inverse part, one moment. To that adjoint inverse, yeah, yeah,
Divided
to
by the
that,
determinant of the matrix.
yes, to that adjoint has to be multiplied to 1 divided by determinant of a. So this is how you get a inverse mathematically. Okay, this is all mathematically, we don't deal with all of this, we can go ahead and directly calculate. For us it's easy, okay, but conceptually, so those are the steps involved to get the inverse of a matrix. For us, inverse of a matrix is very simple. We will see how that is. Np dot random dot rand n. Okay, of, let's just say m comma m. I will supply a value. Again, the reason why I'm writing m comma m is to tell you that the number of rows and columns. Okay, I'm taking as equal. And if you calculate some a, here you'll get some matrix. Okay, and to calculate its a inverse, I will type inva. Okay, so this is nothing but np dot linear algebra dot inverse. Okay, you have inverse directly there, inverse of a. And if you calculate inv of a, and you'll get the inverse directly, inverse matrix, you'll get it. Okay, so and how you get inverse matrix is how you can, what I explained. First you have to go through minor, then cofactor, then adjoint, and to that you have to multiply 1 by determinant of a, so that then you will get the inverse. Now what we are trying to understand is this, a into a inverse is a into inv a. If you multiply, so if you multiply a into a inverse, ideally it has to be identity matrix. Okay, so ideally this has to be identity matrix, but let's do one thing. Plt dot match show of a, this is your a matrix. Okay, plt dot match show of inva, this is your inverse of a, and then uh, plt dot match show of a product of inv a. Okay, now you got it. So even though these values are, if you pay attention, there is e to the power of 0 0, there is e to the power of minus 17, which means there are 17 or 16 zeros before this. Before this 3 there are 16 zeros, which is equal to 0. Okay, because we have taken decimal values, it has done the precision computation, so it has retained those values, but these are almost equal to 0. See, e to the power of minus 16 is 15 zeros follow before this 3. Here 16 zeros follow, here 17 zeros follow. So this way this is equal to 0 only. This is 0 0 0 0. Okay, this is 1 1 and 1. That you can very clearly understand. This is what a looks like, this is what inverse of a looks like. And if you upon multiplication you get only along the diagonal, you will get 1, which is your yellow color, and you get zeros on the um, non-diagonal as non-diagonal elements, which indicate your I. So this established the relationship that a multiplied by inverse of a will always be equal to identity matrix. Okay, this you can tell from the graph itself. Is this clear? Inverse of matrix.
Yes.
Okay.
Yes, yes.
Okay, all right. So if this is understood, then we will go on to the next topic. S- Solving linear equations. Okay, let me conclude the topic here.